A pleasant day to everyone. It's me again, Dr. Marik Neri. I will be discussing today two operations that involve vectors. And these two operations are specifically the dot product and cross product of vectors with some applications. So firstly, let's begin with the dot product. The dot product, or sometimes we call it the scalar product of two vectors A with components A sub 1, A sub 2, and A sub 3, and vector B with components B sub 1, B sub 2, and B sub 3 is denoted by A dot B. So we read it as A dot B. And this is the scalar quantity given by the sum of the product of corresponding components. So you get the product of the first component, and then the product of the second components, and the product of the third components, and you add them up, and that gives you the dot product of the two vectors. For example, suppose that we have these three vectors A, B, and C. So what is the dot product of A and B? So we get the product of the first components of A and B. So that would be 2 times negative 3. And then the product of negative 1 and 2. And then the product of the third components, 4 and 0. And then we multiply them, and then we add, and we get the value negative 8. Another example is the dot product of C and B. So we get the product of the first components, that's negative 3 times 7, and then of 4 times 2, and then of 1 times 0, and we get the products and we add them and we get negative 13. And one more example is, suppose that we have a sum and then we get its dot product with C. Now we may be tempted to perform a distribution operation here. And in fact, that would be allowed, but that would be for later. So what we can do right now is we can get the sum first of A and B. So getting the vector sum of A and B, we have 2 plus negative 3 is negative 1. Negative 1 plus 2 is 1. And 4 plus 0 is 4. Then we get the dot product of this vector sum with C. And we get the products, and then we get the sum of these products, and the answer is 1. Now we emphasize that the dot product is a real value. Okay, it is a number, a scalar value. Now what are properties that govern dot products? So suppose that we have three vectors, A, B, and C, and a real value C, a small c. Firstly, the dot product is commutative. So the vectors may commute. So A dot B equals B dot A. And the proof for this is very simple. It is because when you get the dot product, then each term will be a product of two components, of corresponding components, and the product of these two numbers is commutative. Okay, because multiplication of real numbers is commutative. And so you can switch the positions of the numbers and you will get B dot A. Now the second property is the distributive property of the dot product over the vector addition. And it works similar to our distributive property of multiplication over addition of real numbers. But in fact, the order is the positioning of the vectors is not really important. You can have B dot A plus C dot A because of the first property that the dot product is commutative. And the dot product of A with a scalar times B, you can move the scalar and multiply it to A first, then get its dot product with B. Or you can just get the dot product of the two vectors first, then you multiply it with the scalar C. And the dot product of any vector with the zero vector is the zero number. I want to emphasize on the right side is a number, it's the zero number. On the left side is the 0 vector, okay? And one nice property of the dot product is that the dot product of a vector with itself is the square of its magnitude. So I hope you remember the magnitude in vectors in R3. It refers to the length of the vector. Now, if we have two vectors which are non-zero vectors, we can always draw the vectors from the origin, and we will draw then position representations of the vectors. So these vectors, they will share a common starting point, which is the origin. So from there, we can determine the angle that these vectors make with one another. So it is like the two vectors lie on a single plane, and on that plane, they will form an angle. And what is that angle? It is the least non-negative angle between their position representation. And we want to show that this angle can be obtained by way of the dot product. So we have this theorem. Suppose that A and B are non-zero vectors, and let theta be the angle between them. Then the cosine of theta, or the cosine of the angle between them, equals the quotient of the dot product of the two vectors and the product of their magnitudes. Okay, so in the numerator, you get the dot product, and then in the denominator, you just multiply the magnitudes. Okay, so in our diagram here, we take note that the angle theta is the angle between A and B. And this angle is from 0 to pi. And the vectors A and B are parallel if and only if theta is 0. So in that case, your two vectors point in the same direction. Or if theta is pi, in that case, they point in opposite directions. The vectors A and B are perpendicular or orthogonal if and only if the angle between them is 90 degrees or pi over 2. So for instance, find the angle between A equals 2i minus 2j plus k and B equals I plus k. Now take note that the ij, k's here are unit vectors, and they represent the natural unit vectors in three-dimensional space. So we can rewrite the vectors A to one we are more familiar with. So we can write A as 2, negative 2, 1, and B as 1, 0, 1, because the jth component has coefficient 0. So to get the angle, what do we need? Firstly, we need to get the dot product of the two numbers or of the two vectors and their magnitudes. So we write the dot product in the numerator and the magnitudes in the denominator, and the dot product is 2 plus 0 plus 1, that would be a 3, and the square, the magnitudes will be 4 plus 4 plus 1, 9, you get the square root of that, and 1 plus 1, 2, you get the square root of that. Simplifying, we get 3 over 3 square root of 2, but we can cancel the 3 and we just have 1 over the square root of 2, or that is the same as square root of 2 over 2, which is a special value. It gives us a specific angle. So cosine theta is 1 over the square root of 2, means theta is the value inverse cosine of 1 over the square root of 2, or more familiarly known as pi over 4. So that's the angle made by the two vectors. Let us show that these two vectors are perpendicular. So we write A in the form that we are more comfortable with, 3, negative 2, 3. And B is 1, negative 3, negative 3. Let theta be the angle between the two vectors. And we compute So this is our dot product and the magnitudes. We simplify things. Take note that the numerator, 3 plus 6 minus 9 is 0. So the whole thing becomes 0. So cosine theta is 0. And what theta gives a cosine of 0? Exactly, it is pi over 2. So they form an angle of pi over 2, and that means that the two vectors are perpendicular to one another. Now notice that to determine if the two vectors are perpendicular, in the formula for the cosine, we just need to check the numerator. So if the dot product is 0, then that implies the two vectors are perpendicular, because then the cosine will be 0. So this is our simple check. If the dot product of two non-zero vectors is 0, then the two vectors are perpendicular or orthogonal to one another. Now, let us be careful here. It doesn't mean that the dot product is 0, that one of the vectors is already 0. You can have two non-zero vectors and their dot product is non-zero. And their dot product is 0 provided that these two vectors are orthogonal. Okay, so let's have an example. This is an application in physics, and it is given that the work W done by a force vector F that acts on an object with displacement vector D is given by W equals the dot product of F and D. So take note, this F and that D are vectors. So in our figure here, we can illustrate that the vector F is the red vector and the displacement vector D is the uh, bluish vector. So let's suppose that a wagon is pulled a distance of 50 meters along a horizontal path by a constant force of 60 newtons. The handle of the wagon is held at an angle of 45 degrees above the horizontal. Find the work done by the force. Now, take note that the uh, force and the displacement are vectors, but we don't know what these vectors are. So what is our remedy? Now, since we know the angle is 45 degrees, we can make use of the cosine formula. And this is just the same as distributing or cross-multiplying the uh, denominators, which are the product of the magnitudes, to cosine theta. Okay, so I repeat, you have cosine theta equals dot product over magnitudes. So if you cross multiply the magnitudes to cosine theta, you get dot product. All right, so dot product of F and D equals cosine theta times the product of the magnitudes. So the magnitude of F is what's given here. It is the constant 60 newtons, and the magnitude of D is what's given there as 50 meters. The angle is 45 degrees. So putting the values here, cosine of 45 degrees is the square root of 2 over 2. So we can simplify things and we get 1,500 square root of 2 Newton meters. So that is the work done by the force with the displacement D. Okay? Now let us go to something that we frequently notice when we have an object and a light is cast on the object. A light is, uh, you shine a light on the object, and then the object will cast a shadow. So usually we say that that shadow is a projection of the object. So in mathematics, we have a formal term for projection. Okay, so suppose that we have two non-zero vectors A and B. The vector projection of B onto A, okay, so it's like the vector B casts a shadow on the vector A, right? So what will be that shadow? We call that the vector projection of B onto A, and it is given by this notation, projection, so that's proj of B sub A, and this is equal to the dot product of A and B over the magnitude of A squared times the vector A. And this projection is the perpendicular projection of the position representation of B onto the line containing the position representation of A. Now take note that the projection can be done in two ways. So if the two vectors form an angle which is acute, then the projection will be in the direction of A. Okay, so this is our first figure here. And otherwise, if the two vectors form an angle which is obtuse or greater than 90, then the projection will be on the other side or on the reverse direction of A. Now, we want to emphasize that the projection is parallel to A. Okay, and that's why in the definition itself, we see the scalar, which is the dot product over the magnitude squared. So this expression here is just a real number times the vector A. So the projection is parallel to the vector A. Okay, so as I had said earlier, if the angle they make is acute, then the projection of B onto A is in the same direction as A. If the angle they make is pi over 2, then the projection of B onto A is just the zero vector. It's just like you're standing at midday and the sun is directly up ahead, and then the shadow cast is straight to your foot. So we say it's shadowless. Okay? So in mathematics, if your B is perpendicular to A, then the projection is the zero vector. Or it's just you cannot say it's a point, it's just a zero vector. There is no projection. Oh, let me correct that. There is a projection, but it is the zero vector. If the angle they make is obtuse, then the projection of B points in the opposite direction of A. For example, consider these two vectors A and B. So let us determine the vector projection of B onto A, and what will be the vector projection of A onto B. So firstly, we get the dot product of A and B. And that dot product is given by the value 4. The magnitude of A is the square root of B, and the magnitude of B is the square root of 6. Okay? So the projection of B onto A would be parallel to the vector A. So that's why you should have the vector A here. And then you just get the dot product and over the scale, over the square of the magnitude. And that's what we have. On the other hand, the projection of B onto A, or the projection of A onto B, is A dot B over the magnitude of B squared times the vector B, because now this will be parallel to the B vector. So again, you just plug the values there, and this is our projection of A onto the vector B. Another example. Let us express the vector A as a sum of a vector parallel to B and a vector perpendicular to B. Okay, I hope you understand what we're trying to get here. You want to show that A is a sum of a vector parallel to B and perpendicular to B. Okay? So take note that the projection of A onto B is parallel to B. So that already gives us an idea of what vector to use. So let's just get the projection of A onto B. And that is given by these values here times the vector B, and we get negative 2, 1, 2. Now, take note that I can have some vector C, and this vector C I will define as A minus the projection of A onto B. Okay? So later we will show why this is so. So let me just get the difference of A and its projection. And this is equal to 4, 2, and 3. Now question, is this C perpendicular to B? Well, we can do a quick check by just taking the dot product of B and C. So we get there an 8, and then we have a minus 2, so that's a 6, and then we have a minus 6, and that's a 0. So C there is orthogonal to the vector B. And so by what we have in our equation here, we can say now that A is equal to, if we cross or if we transpose the projection of A onto B to the left side of the equation, we get A equals C plus the projection. Okay? And the projection of A to B is given by negative 2, 1, 2, and the value of C is 4, 2, 3. And you can verify that when you take the sum, this is equal to 2, 3, and 5. Now, what's the basis for C? No? Baka sabihin nyo, sir, paano namin may isip yung difference na yan? Well, it's simply a matter of the properties of vectors. So consider the diagram. We have a vector B here, the vector A there. And since A dot B, if you notice A dot B in our equation here is 4 minus 3 minus 10. That's a negative 9. So it's negative. So A and B form an obtuse angle. So the projection of A onto B will be in the opposite direction of B. So that's the blue ray there. So that's the projection of A onto B. And the angle from the head of the projection of A onto B to the head of the vector A is the difference. So A minus that vector. Okay? And since this is the projection of A onto B, then the vector A minus projection of A onto B is orthogonal with that projection. Okay? So that's how we got this C equals A minus the projection of A onto B. Okay, so now I hope the dot product is clear with you, as well as its applications in the cosine of the angle between two non-zero vectors. Let us go to another operation, which is called the cross product. So by definition, the cross product of two vectors, A and B, we denote that by A cross B, or you may say A times B, but this is not multiplication of numbers. So better say A cross B. This is the vector given by, so we have here a notation again. This is a symbolism. There's really no mathematical operation being done here. It is just a presentation. And this notation or this presentation is defined by these three terms here. Okay? Now, the number, the two bars containing your array of numbers inside, or your matrix, is called the determinant of that matrix. So what we do is, to get the cross product of A and B, first we take the determinant of the last two columns, okay? And then minus, so it's like we cover the middle column and get the determinant of the first and the last column. But we put a minus sign here. And lastly, for the third component is we cover the third column and we get the determinant of the first two columns, and that will be our kth component. So the definition will be, you get the product of the main diagonal minus the product of the off diagonal. That's what we have here. That's your first component. And here you get the product of the main diagonal less the product of the off diagonal. But then you multiply by a negative sign. So that's why we have a change in positions here. That's the second component. And the last one is you get the product of the main diagonal minus the product of the off diagonal, and that will be our third component. Okay, so it seems like medyo marami tayong kailangan tandaan for the cross product. Ganun talaga yon. No? Basta isipin mo lang, if you are getting the first component of the cross product, you cover the first components of the numbers and you work on the last two components. When you get the second component, you cover the second components and work on the first and the third components. And when you are looking for the third component, you cover the last component and you deal with the first two components. So ganun yun. Okay? So you apply the cross product only on pairs of vectors. So some properties of the cross product. So let A, B, and C be vectors and small c be a real number. The cross product is not commutative. We emphasize that. It is not commutative, meaning the cross product of A and B is not the same as the cross product of B and A. Okay? Rather, the cross product of A and B equals the negative of the cross product of B and A. So if you commute the two vectors in a cross product, you get a negative sign as an off result. But as with the dot product, the cross product is distributive over vector addition and also vector subtraction. You can also move around a scalar multiplied to a vector. So the cross product of A and C times B is the same as you just get the cross product of A and B first, then you multiply by C. The cross product of a vector A with the zero vector is the zero vector. Now we emphasize this is not the zero number. This is the zero vector. So the cross product is always a vector, whereas the dot product is a real number. The cross product of a vector with itself is the zero vector. Okay? So for example, let this be our two vectors A and B. So the cross product of A and B, so what we do is we can set up this expression here. So for the first component, we cover the first column, and then we deal with the second and third columns. We get the products, 3 times negative 5 minus 7 times 4. And then we cover the second column. and then deal with the first and last. So that, but then we put a minus sign there. So that's a negative 5 minus 8, j. And lastly is we cover the third column and work with the first two columns. We have a plus 7 minus 6. And when you simplify the sum, you get this vector. Now, how about B cross A? By the theorem, we expect that this will be the negative of A cross B. Okay. Is that really the case? So let's check. So if you get the cross product of B and A, so you get 28 minus 15, so that becomes a plus 15 there. Minus, you get a 2 times 4, that's an 8, minus 5, that's a plus 5. And then plus, you get a 2 times 3, 6, minus 7, what we have here. And this is 43, this is minus 13, and that is negative 1. If you compare that with the first cross product, we get the negative, which validates our theorem. Now, when the dot product is related to the cosine of the angle between two vectors, the cross product, on the other hand, is related to the sine of the angle between the two vectors. And we have a theorem, the following. The magnitude of the cross product of A and B is the product of the magnitudes of A and B times the sine of the angle between the two vectors. Take note that if sine theta is 0, which happens when theta is 0, then the two vectors are parallel because the angle between them is 0. So they are parallel, and that makes the right side 0. So the cross product of A and B, the magnitude is equal to 0. And we have a property for magnitudes. The magnitude of a vector is 0 if and only if the vector is the 0 vector. So if your right-hand side here becomes 0 because the two vectors are parallel, then the cross product will also be the 0 vector. So the cross product of parallel vectors is the 0 vector. Now, the 0 vector, by extending the definition of a cross product, is considered to be parallel and also perpendicular to all vectors. Because if you get the dot product of any vector with 0, the answer is 0. So they are perpendicular. If you get the cross product of any number with 0, you also get, of any vector with 0, you also get the 0 vector. So they are parallel. One nice application of the cross product is that it gives us a way to find the area of a parallelogram with sides A vector and vector B. This area is simply the magnitude of the cross product. Now, why is that so? If you look at the diagram here, how do you get the area of a parallelogram? It's very simple. You just get the base, and then you multiply that by the height of the parallelogram. Now, the length of the base is simply the magnitude of A. The length of this side is just the magnitude of B. If you drop a perpendicular to the base, then using your Sohcahtoa rule, okay, so the opposite side of this theta, okay, will be the magnitude of the vector B times the sine of theta. Okay, so that follows from our rules in trigonometry. And so the area now of this parallelogram is the product of this length of the base and the length of the altitude. And that is exactly the formula that we have here in the theorem. It's the magnitude of A times the magnitude of B sine theta, and that by theorem equals the magnitude of the cross product. Okay? So for example, Find the area of the triangle with vertices at the points A, B, and C. So I drew a sketch of these points. Now, to get the area of the triangle, uh, we can form the triangle by just connecting the points with line segments. And take note that the area of a triangle is always half the area of a rectangle. All right? So what we can do here is we first get the area of the parallelogram. Take note, a rectangle is also a parallelogram. We take the area of the parallelogram determined by two vectors AB and AC. Okay, so these two vectors here. We get the area of that parallelogram, divide that by 2, and that gives us the area of the triangle. So the parallelogram will look like this. So you have here, if you just reflect this side here about the line BC, you get the other side of the other part of the parallelogram. So let's get the two vectors AB and AC. And that's easily done by subtracting. I hope you remember, you just get the head minus the tail. So the vector AB is 3 minus 1, that's 2. We get a 1 minus 2, that's negative 1, and a 10 minus 4 is 6. Similarly with the vector AC. So to get the area of the parallelogram determined by the vectors AB and AC, we just get its cross product. Okay, and the cross product is the vector negative 8, 8, 4. And then we get the magnitude of that cross product, and that is equal to 12. So what's the area now of our triangle? It is half the area of the parallelogram, and it is 6 square units. So the area of the triangle with these vertices is 6 square units. Now it helps to remember property that the cross product is always orthogonal or perpendicular to both A and B. Okay, so that's very nice. The cross product of A and B is orthogonal to both A and B. And for this, we apply the right-hand rule. Okay, the right-hand rule is not new to us. We already introduced this when we studied our vectors, our three-dimensional system. So if this is your vector A and this is your vector B, then the cross product is the vector A cross B. Okay, so that's your right-hand rule. So in this sense, para bang sinasabi natin, if the vector A is I and the vector B is J, then the vector A cross B is I cross J equals K. Yun yung implication nun. Let's have an example. Find two unit vectors perpendicular to both A vector and the B vector. So one perpendicular vector to both A and B is the cross product by the theorem that we have. So we just get the cross product, and that cross product is 1, 2, and negative 1. When we say a unit vector, that means the magnitude is 1. So all we do is simply multiply the vector C with the reciprocal of its magnitude, or we just divide by its magnitude. Okay, and this is what we get. So this is the vector U sub C. This vector is a unit vector. It is orthogonal to both vectors A and B because it is a unit vector in the direction of the cross product. What will be the other unit vector? Well, if I have this vector is perpendicular to this vector, then this vector will also be perpendicular to this vector. So to get this vector, I just get the negative, put it in the opposite direction. So the negative of u sub c will also be perpendicular to A and B. Okay? So let's go now to a set of exercises. So for the first set, we want to determine the vector parallel to B. So we want to measure some angle and a vector projection. Number 2 is a proving part. And number 3 is we will be applying here the cross product because we will be looking at the area of the parallelogram. So I prepared some solutions to these exercises. So for the first one, given the vectors A and B, where B is PQ and P is given by these 2 points, and C is given by this vector also. Find the unit vector in the same direction as B. So what we need to do is first get the vector B. So what is the vector B? It is PQ, where Q is the head and P is the tail. So we just have 5 minus 1, 1 minus 1, and negative 1 minus 1, and that is 4, 0, minus 2. The unit vector will be, we just divide B by its magnitude, and the magnitude is 16 plus 4, 20. We have the square root of that. That is 2 square root of 5. And then we simplify things, we get this vector here. Now for the second problem, what is the measure of the angle between the vectors B and C? So for that, we need to determine the cosine. So using the dot product of B and C over the product of their magnitudes, this is what we have. The dot product gives us negative 2. And this will be our magnitudes. So we can just cancel the 2 and then get the inverse cosine. Negative 1 over square root of 55 is not a special value, so we just leave the answer in this form. So theta is inverse cosine of negative 1 over the square root of 55. Okay? For the second problem, this is the third problem. What is the vector projection of the vector A onto the vector C? So it will be parallel to the vector C, so that's why you have a C there. And we just perform the operations indicated. Get the dot product, that will be a 10. Magnitude of the denominator squared is 11. And then multiply by 2, negative 1, 3, and that's it. Okay, or you can just have a 20 over 11, a negative 10 over 11, and a 30 over 11. Or we can just leave it in this form. That will be fine. Okay. So suppose that A and B are non-zero vectors. Show that the vectors projection of A onto B and A minus the projection of A onto B are perpendicular. Now, I will not show you the proof line by line, but this is what we should do. You must show that the projection of A onto B and projection of A minus the projection of A to B is 0. I forgot to put the 0 there. This should be equal to 0. Okay? This is equal to 0 using the following properties. So the first property should be obvious. You'll be distributing the projection of A to B to these two values here. And then you can use the definition for the projection. You will have scalars appearing there. And use the property here. And then use the commutativity property. And the last would be the property that the dot product of a vector itself equals the square of the magnitude of that vector. Okay? And then you must be able to show that this dot product equals 0. Then you conclude they are perpendicular. Now for the last set, consider these points A, B, and C, and the parallelogram with AB and AC as edges. So find the coordinate of the fourth vertex D of the parallelogram. So you can imagine you have a point A, B, C. So you have a point D there. So that D should be parallel to AB. So let D will have components or coordinates x, y, z. So again, the AB, the vector AB should be parallel to the vector CD. Okay? So they must have equal lengths in the parallelogram, and they must have exactly the same vectors. Okay? So if they have the same lengths and they have the same direction, they are the same vectors. So the vector AB is 6 minus 4, 2, 3 minus 7, negative 4, 0 minus 2 is negative 2. And the vector CD is x minus 7, y minus 1, and z minus minus 3. And then two vectors are equal if their corresponding components are equal. So you just equate x minus 7 to 2, y minus 1 to negative 4, and z plus 3 to negative 2. And you get x equals 9, and y equals negative 3, and z equals negative 5. So this will be the point D, 9, negative 3, negative 5. Find the area of the parallelogram. So to get the area, we just need two vectors that determine the parallelogram, and that vector, those vectors will be the vector AB and the vector AC. So the vector AB is already given. We already know the vector AB here. Then we can compute the vector AC. So the vector AC is just 7 minus 4, that's a 3. 1 minus 7, that's a negative 6. And negative 3 minus 2, that's a negative 5. And then you get the cross product of that AB and AC. And what we get is this vector. You get the magnitude of that, and that becomes the area of the parallelogram with the two edges. Okay? So that ends our discussion for these two operations that involve vectors. You will be encountering this more often as you go to higher mathematics. So I hope that you remember these two important vector operations. So for now, that's everything. So have a pleasant rest of the day.